asked to find the limit of the sequence given by a sub n. Looking at the theorem below, if a sub n equals f of n, and the limit as x approaches infinity of f of x equals L, then a sub n converges to L, and the limit as n approaches infinity of a sub n equals L. So this theorem is telling us we determine the limit of a sequence the same way we determine the limit at infinity of a function. Instead of formally defining a function f of x, or f of n equals a sub n, we often just let the formula for a sub n be a function of n and determine the limit as n approaches infinity of, in this case, the quantity 7n squared plus n plus 3 divided by the quantity 6n squared plus 5n plus 4. Now there are several ways to determine the limit at infinity of a rational function. In this video, we'll take a look at the general method as well as a shortcut method. So for the general method, we divide each term in the numerator and denominator by the highest power of x, or in this case, the highest power of n, in the denominator, and then we find the limit at infinity in the new form. So looking at the denominator, notice how the highest power of n is n squared, so we'll divide each term in the numerator and denominator by n squared. This will give us the limit as n approaches infinity of, in the numerator we'd have 7n squared divided by n squared plus n divided by n squared plus 3 divided by n squared. In the denominator we'd have 6n squared divided by n squared plus 5n divided by n squared plus 4 divided by n squared. And now we simplify each fraction, so we have the limit as n approaches infinity. 7n squared divided by n squared simplifies to just 7. N divided by n squared simplifies to 1 over n to the first, or just 1 over n. This fraction does not simplify. 6n squared divided by n squared simplifies to 6. 5n divided by n squared simplifies to 5 over 1 factor of n, and 4 over n squared does not simplify. So in the numerator we have 7 plus 1 over n plus 3 over n squared. In the denominator we have 6 plus 5 divided by n, or 5 over n, plus 4 over n squared. And now the idea is we can determine this limit in this form. We'll notice the 7 and the 6 are not affected by n, but these four fractions are all going to approach 0 because the numerators are constants, and the denominators contain either 1 or 2 factors of n, and therefore the denominators are increasing without bound as n approaches infinity. So this fraction approaches 0, this fraction approaches 0, this fraction approaches 0, and so does this fraction. And again, the 7 and 6 are not affected by n, and therefore the limit is equal to 7/6, which means a sub n converges to 7/6, which means as we generate more and more terms in the sequence using this formula, the terms approach a value of 7/6. Before we look at this graphically, let's determine this limit again using the shortcut method. So beginning with visual limit, by analyzing the degree of the numerator and denominator, we can also determine this limit. So the shortcut method tells us that if the degree of the numerator is less than the degree of the denominator, then the limit of the rational function is 0. If the degree of the numerator and denominator are equal, the limit is equal to the ratio of the leading coefficients, and if the degree of the numerator is greater than the degree of the denominator, the limit does not exist. Well, notice how the degree of the numerator is 2, the degree of the denominator is 2, so because the degree of the numerator and denominator are equal, this limit is equal to the ratio of the leading coefficients, which would be 7/6. And now let's look at this sequence graphically. This graph shows the terms in the sequence where we have n along the horizontal axis and a sub n along the vertical axis. Notice as we generate more and more terms, the terms do seem to approach a particular value, which in this case is 7/6, and 7/6 is approximately 1.17, and notice how here we have 1.2 on the vertical axis. So it does appear from the graph the terms in the sequence are approaching the value of 7/6. I hope you found this helpful.